Imagine you're hiking and you stumble upon something incredible. A skull, massive, with teeth like daggers. Your first thought? It must be a dragon, a griffin, a giant from myth. For most of human history, this wasn't just imagination. It was the most logical explanation. Welcome to the world before paleontology, a time when stones told tales of monsters, not of natural history. For thousands of years, people all over the world found strange, stony remains embedded in rock. In ancient Greece, the massive bones of mammoths were believed to be the skeletons of heroes from the Trojan War. In China, what we now know as dinosaur bones were called dragon bones and were ground up for traditional medicine. The legendary Cyclops? Some scholars believe that myth originated from ancient Greeks, finding the skulls of dwarf elephants in caves. Their large central nasal cavity, where the trunk attached, looked exactly like a single giant eye socket. These weren't just stories. They were attempts to make sense of a world filled with baffling evidence. Fossils were curiosities, omens, or proof of mythological beings. They were anything but the remains of ancient life. So, when did this change? When did a dragon's tooth become a megalosaurus tooth? The shift was gradual, a slow-burning revolution in human thought. It began with curiosity, the same feeling you'd have finding that strange skull on your hike. During the Renaissance, thinkers like Leonardo da Vinci looked at seashells high in the mountains and correctly deduced that these areas were once seabeds. He was one of the first to argue that fossils were the remains of once living organisms. But his ideas were radical and far from mainstream. The prevailing view, heavily influenced by religious doctrine, was that these were either tricks of nature, placed in the rock by some mysterious force, or remnants of creatures that perished in a great global flood. The key turning point arrived in the 17th century with a Danish scientist named Nicholas Steno. While dissecting the head of a massive great white shark, he noticed its teeth bore a striking resemblance to mysterious triangular stones called tongue stones, or glossopetrae, which were commonly found embedded in rocks. For centuries, people believed these were the petrified tongues of serpents. Steno made the crucial connection. He argued that these stones were, in fact, ancient shark teeth. This was a monumental leap. He proposed that the rock surrounding the fossil must have been soft sediment that hardened later. This simple, elegant observation laid the groundwork for stratigraphy, the study of rock layers, which is fundamental to understanding geological time. For the first time, a fossil wasn't a mythological artifact. It was a piece of data, a clue to a past world. The stones were beginning to speak a new language, the language of science. This new way of thinking sparked a firestorm of debate. If these were extinct animals, what did that mean for the idea of a perfect, unchanging creation? The concept of extinction was deeply unsettling. One of the greatest champions of this new science was Georges Cuvier, a brilliant French naturalist working in the late 18th and early 19th centuries. Known as the father of paleontology, Cuvier was a master of comparative anatomy. He could look at a single fossil bone and, by comparing it to the skeletons of living animals, reconstruct the entire creature. He examined the massive bones being dug up around Paris and proved, beyond any doubt, that they belonged to animals like mammoths and mastodons, elephants, yes, but of a kind that no longer existed. He was the man who scientifically established extinction as a fact. The world, he argued, had gone through revolutions, catastrophic events that wiped out entire species, paving the way for new ones. Cuvier's work electrified the public. Suddenly, monster hunting was no longer the stuff of legends. It was a scientific pursuit. The early 19th century became the heroic age of paleontology. Bone collectors and fossil hunters fanned out across the globe. In 1822, an English country doctor named Gideon Mantell and his wife Mary Ann found some enormous fossil teeth in a quarry. They didn't resemble any known mammal. After much consultation and debate, Mantell realized they belonged to a gigantic, extinct reptile. He named it Iguanodon because the teeth resembled those of a modern iguana, but vastly larger. Soon after, William Buckland, a professor at Oxford, described Megalosaurus, the great lizard, based on a massive jawbone. And then came the discovery of the first marine reptiles, the Ichthyosaurus and Plesiosaurus, by a remarkable young woman named Mary Anning, a self-taught fossil hunter from a poor family on the English coast. Her incredible finds challenged the very idea of what ancient life looked like. These weren't just big lizards. They were sea dragons, brought from myth into the realm of reality. The word dinosaur, meaning terrible lizard, wasn't even coined until 1842 by the scientist Richard Owen, who realized that Iguanodon, Megalosaurus, and another new find, Haleosaurus, shared common features that set them apart from all other reptiles. He envisioned them not as sprawling lizards but as active, dynamic creatures. This was the moment the modern image of the dinosaur was born. The scattered bones were no longer just individual curiosities. They were becoming part of a coherent, lost world, a Jurassic Park of the scientific imagination. The shift was complete. Fossils were no longer omens or monsters. They were evidence. Each bone, each tooth, each footprint preserved in stone was a word, a sentence, a chapter in the epic story of life on Earth. The journey from myth to museum, from dragon to dinosaur, wasn't just about digging up bones. It was about learning to listen to what they had to say. It was about developing a new kind of curiosity, one that wasn't satisfied with legends, but demanded evidence. It's a curiosity that drives science to this day, as we continue to uncover the secrets of the stones that, after millennia of silence, finally began to speak. Have you ever wondered how we figured out that the Earth is billions of years old? For a long time, most people, especially in the Western world, believed our planet was just a few thousand years old, based on religious texts. But then we started digging, and what we found in the ground would completely rewrite the story of time itself. It all started with rocks. In the 18th and 19th centuries, geologists like James Hutton and Charles Lyell looked at canyons, mountains, and layers of sediment. They realized that the slow, steady processes they saw happening today, like rivers carving valleys or sand turning to stone must, have been going on for an incredibly long time to create the landscapes we see. This idea, called uniformitarianism, suggested an Earth far older than anyone had imagined. But this was just the first clue. The real bombshell came from the fossils. People had been finding strange stony objects for centuries, often calling them dragon bones or thunderstones. But as the science of anatomy developed, scholars like Georges Cuvier in France began to understand what they really were: the petrified remains of extinct animals. Cuvier studied giant mammoth skeletons and massive sea reptiles called mosasaurs. He proved beyond a doubt that entire species had lived and died out long ago. This concept of extinction was revolutionary. It meant the world hadn't always been the way it was. It had a deep, hidden history. Each layer of rock seemed to tell a different chapter of this history. Lower, older layers held bizarre creatures like trilobites, while higher, younger layers contained fossils that looked more like modern animals. It was like a library of life, with each rock stratum as a different book. This fossil record showed a clear progression, a story of life changing over immense periods. The idea of deep time was no longer just a geological theory. It was written in stone and bone. But there was one major piece missing from this ancient puzzle: us. While scientists were finding dinosaurs and mammoths, there was no sign of ancient humans. The prevailing belief was that humanity was a recent creation, appearing only in the very last chapter of Earth's history. According to the accepted timeline, humans had only been around for about 6,000 years. Finding any human remains alongside extinct animals would shatter that entire worldview. And that's exactly what happened. In the 1830s and 40s, a French customs official, an amateur archaeologist named Jacques Boucher de Perthes, started digging in the gravel pits of the Somme Valley. Among the bones of mammoths and woolly rhinos, he found something extraordinary: crudely shaped stone tools. He argued that these weren't natural rock formations. They were hand axes, made by humans who must have lived at the same time as these extinct Ice Age beasts. At first, the scientific community laughed him off. The idea was too radical. The religious and academic establishments were deeply invested in the young Earth, recent humanity model. How could primitive people have coexisted with creatures from a supposed pre-human world? For nearly 2 decades, Boucher de Perthes was dismissed as a crank. But the evidence kept piling up. In 1856, workers in Germany's Neander Valley stumbled upon a strange skeleton. It had a thick, sloping brow ridge, a robust build, and a skull shape different from any modern human. This was the first recognized Neanderthal. Was this an ancient, primitive human? Or just a diseased modern one? The debate raged. The turning point came in 1859. The same year, Darwin published On the Origin of Species. A team of respected British geologists, including Joseph Prestwich and John Evans, traveled to France to see Boucher de Perthes's sites for themselves. They carefully excavated the area and saw with their own eyes stone tools embedded deep in undisturbed soil layers right next to the bones of extinct Ice Age mammals. There was no way to explain it away. The evidence was irrefutable. They returned to London and, at a meeting of the Royal Society, declared their support. The scientific world was stunned. If humans had made tools to hunt mammoths, then humanity itself had to be ancient. The 6,000-year timeline for human history instantly collapsed. It wasn't just a matter of adding a few thousand years. It was a complete paradigm shift. The antiquity of man was now a scientific fact. This discovery opened the floodgates. Suddenly, archaeologists were re-examining old finds and actively searching for new ones. More Neanderthal skeletons were found, along with other early human relatives like Cro-Magnon in France. These weren't just isolated oddities. They were part of a long, complex human story that stretched back tens, even hundreds of thousands of years into the past. The combined force of geology and paleontology had rewritten time. The Earth wasn't thousands of years old, but millions, and eventually we'd learn billions. And humanity wasn't a recent arrival, but an ancient lineage, with roots deep in the Ice Age and beyond. The bones and stones buried beneath our feet had forced us to accept a reality far grander and more ancient than we had ever conceived. They revealed our true place in the vast epic story of life on Earth. It's a powerful reminder that science is a process of discovery, often challenging our most cherished beliefs. The story isn't over. We're still digging, still finding new fossils that push back the timeline and add new characters to our family tree. Each discovery is a new page in the incredible biography of our planet and ourselves. Ever feel like you're trying to solve a puzzle with most of the pieces missing? Well, welcome to the world of paleoanthropology. When we imagine discovering our ancient ancestors, we might picture a complete skeleton, laid out perfectly, just waiting for us. But the reality? It's a lot more crumbly. Most of the time, what we find isn't a full skeleton, but a single tooth, a piece of a jaw, or a fragment of a skull. And these tiny, scattered pieces are the clues we use to reconstruct the vast epic story of human evolution. Think about it. The entire history of our lineage, stretching back millions of years, is built on a collection of fragments. Take Lucy, for example. Discovered in 1974, she was a sensation because her skeleton was about 40% complete. 40%! That was considered an incredible treasure trove of information. Before and after Lucy, many groundbreaking discoveries have been based on far, far less. A few teeth found in a cave can tell us about an ancient hominin's diet. A single oddly shaped foot bone can reveal whether a creature walked upright. It's like being a detective with the coldest of cold cases. Let's talk about some of these game-changing fragments. The famous Tong child, found in South Africa in 1924, was just a fossilized skull of a young individual. But it was revolutionary. It had a small brain like an ape, but its teeth and the position of its spinal cord entry point suggested it was an upright walker. This was the first evidence that bipedalism, walking on two legs, might have evolved before our big brains. It completely flipped the script on what we thought it meant to be human. At the time, many scientists were skeptical. How could this small-brained creature be our relative? But that one small skull fragment forced a huge shift in our understanding. Or consider the discovery of Homo habilis, the handy man. This species was named based on a collection of fragmented fossils found in Tanzania, including parts of a hand, a foot, and a lower jaw. The hand bones were crucial. They showed a precision grip, capable of making and using stone tools. Before this, tool use was thought to be exclusive to species with much larger brains, like our own. But these few bones suggested that the ability to craft tools emerged much earlier in our family tree, again before the dramatic expansion of our brains. It is amazing how a few small hand bones can completely redefine a fundamental aspect of human history. Then there are the Denisovans, a mysterious group of ancient humans we know about almost entirely from a few tiny fragments found in a Siberian cave. I'm talking about a single pinky bone and a couple of molars. That's it. It sounds like nothing, but from that one tiny finger bone, scientists were able to extract ancient DNA. The results were mind-blowing. They revealed a completely new branch of the human family tree, distinct from both Neanderthals and modern humans. This DNA also showed that Denisovans interbred with our ancestors, and their genes live on in some populations today. A whole chapter of human history, a lost world of ancient relatives, was unlocked from a bone smaller than a coin. Each discovery, no matter how small, adds a new piece to the puzzle. Sometimes a new piece fits perfectly where we expect it to. Other times, a fragment comes along that doesn't fit anywhere. It forces us to rethink the entire picture, to question our assumptions, and to redraw the human family tree. That's what's so exciting about this field. The story is never finished. For example, the discovery of Homo floresiensis, the so-called hobbit in Indonesia, presented us with a tiny, small-brained hominin that lived until surprisingly recently. Its existence alongside modern humans was a total shock to the system. How did it get there? How did it survive for so long? These are questions that arose from a partial skeleton and a few other bones. This fragmentary nature of the fossil record teaches us something incredibly important: humility. We have to be comfortable with not knowing everything. We have to be willing to say, "I don't know," or "Our current theory might be wrong." Every fossil is a precious data point, but it's just one point. We're building a grand narrative from whispers and echoes from the deep past. It's easy to get attached to a particular theory, to want the story to be simple and linear. But the fossils keep reminding us that evolution is messy, branching, and full of dead ends and surprising twists. Our knowledge is like a connect-the-dots picture where we only have a few of the dots. We can draw lines between them, creating a plausible image, but we have to accept that the true picture might be far more complex. A new dot could appear tomorrow and change the entire shape. This is what makes science so dynamic. It's not a collection of unchanging facts, but a process of discovery, revision, and refinement. The gaps in our knowledge aren't failures. They are invitations for future generations of scientists. They are the mysteries that drive us to keep digging, keep searching, and keep questioning. So the next time you see a headline about a new human ancestor, remember the reality behind it. It's likely not a whole skeleton, but a piece of one. A fragment that someone painstakingly excavated, cleaned, and studied for years. And remember the courage it takes for scientists to propose a new idea based on that single piece of evidence, knowing it could upend decades of thinking. The story of us is written in these pieces, each one a testament to survival, adaptation, and the relentless journey of life. And with every new fragment unearthed, the story gets a little clearer, a little richer, and a whole lot more interesting. Have you ever looked at a skeleton and just seen, well, a pile of bones? What if I told you that skeletons are actually diaries, written in bone, telling incredible stories about how ancient people lived, loved, and even cared for each other? It's true. Bioarchaeologists are like detectives, and they can read these bone diaries to uncover secrets of the past that history books might have missed. Let's start with the basics. Your bones are amazing. They're constantly changing throughout your life in response to what you do. If you're a professional tennis player, the bones in your serving arm will actually be thicker and stronger than in your other arm. If you spend a lot of time squatting, you might develop specific facets on your ankle bones. Archaeologists can see these same patterns in ancient skeletons. They can look at a skeleton and say, "Wow, this person spent a lot of their life grinding grain." Or, "This person was likely a long-distance runner." It's like reading someone's life story directly from their remains. The skeleton tells us about their daily grind, their habits, and their profession. But it gets even more detailed. Bones can also bear the unfortunate marks of violence. A healed fracture on a forearm, for example, is often called a perifracture. It's a classic defensive injury you get when you raise your arm to block a blow. Multiple healed injuries might suggest a life filled with conflict, or maybe just a very clumsy individual. But sometimes the evidence is much clearer. An arrowhead embedded in a rib cage or a skull with a clear cut from a sword tells a direct and tragic story of a violent encounter. By studying the patterns of these injuries across a whole cemetery, archaeologists can piece together a picture of warfare, raids, or even periods of peace in a society. It helps us understand the challenges and dangers people faced centuries or even millennia ago. Now, this is where the story takes a fascinating and heartwarming turn. We often have this image of ancient life as being survival of the fittest, where only the strongest survived. But the skeletons tell a very different, more compassionate story. Archaeologists have found numerous skeletons of individuals who had debilitating injuries or diseases, things that would have made it impossible for them to hunt, farm, or even feed themselves. Yet, their bones show they lived for years, sometimes even decades after their injury. Think about what that means. A person with a shattered leg that healed poorly would have needed someone to bring them food and water, protect them from predators, and help them move. A person who lost all their teeth would have needed someone to prepare soft food for them. The very existence of these individuals is powerful, silent evidence of care and compassion in the past. It shows that people didn't just abandon the weak or injured. They invested time and resources to care for them. One of the most famous examples is the Old Man of Shenadar, a Neanderthal skeleton found in Iraq. This individual had a crushed eye socket that likely left him blind in one eye, a withered arm that was probably useless, and severe arthritis. He would have been at a huge disadvantage. Yet he lived to be around 40 or 50 years old, which was a ripe old age for a Neanderthal. The only way he could have survived for so long is if his group actively cared for him. This isn't an isolated case. We see similar evidence across different cultures and time periods. These skeletons are monuments to the power of community and social bonds. This evidence completely flips the script on the brutish caveman stereotype. It suggests that cooperation and empathy aren't modern inventions. They are deeply rooted in our human and even pre-human history. The ability to care for others in the group, to support those who couldn't support themselves, might have been one of the most important survival strategies of all. It strengthened the community, ensuring that valuable knowledge and experience held by older or injured individuals weren't lost. So survival wasn't just about being the strongest hunter or the fiercest warrior. It was also about being part of a supportive network. It was about kindness. The archaeological record shows us that compassion is one of humanity's oldest and most successful traits. Our ability to form communities and care for one another is just as crucial to our story as the invention of tools or the discovery of fire. These bone diaries also reveal other aspects of ancient life. We can study diet by analyzing the chemical isotopes in the bone, figuring out if someone ate mostly meat, fish, or plants. We can track the spread of diseases. We can even see evidence of medical treatments, like trepanation drilling a hole in the skull where the bone shows signs of healing, meaning the patient survived the surgery. Every skeleton has a unique story to tell. It's a personal biography of a life lived long ago. But when we look at them together, they tell us the grand sweeping story of humanity itself. They show us that our ancestors were not just struggling to survive. They were complex people who worked, fought, and most importantly, cared for one another. They remind us that the foundations of our societies are built not just on strength, but on cooperation and compassion. So the next time you see a skeleton in a museum, don't just see a collection of bones. Look closer. Try to imagine the person they once were. Think about the life they lived, the challenges they faced, and the people who cared for them. You're not just looking at the past. You're looking at the very essence of what it means to be human. Have you ever wondered what connects you to the dawn of humanity? It's not just a philosophical question. The answer lies buried deep within the earth, in the form of ancient bones. These aren't just dusty relics. They are the very foundation of our modern identity, a living echo from a world long past. Let's journey back in time. Imagine a world without written records, a world where the only stories are told by fossils. When we unearth the remains of our distant ancestors like Lucy, the famous Australopithecus, we're not just finding bones. We're discovering chapters of our own story. These discoveries give us a profound sense of continuity, a lineage stretching back millions of years. They show us where we come from. Knowing that our ancestors walked the African savanna, developed tools, and formed social bonds helps us understand the innate behaviors that still drive us today. Our desire for community, our instinct to create and innovate, it all started there. These bones give us a shared origin story, a common heritage that transcends modern cultures and borders. We are all part of this incredible human family, and the proof is written in stone and bone. Think about the moment the first Neanderthal skull was found. Suddenly, we weren't the only humans to have ever walked the earth. This discovery radically changed our perception of ourselves. It forced us to ask new questions. Who were they? How did we interact with them? And what does their extinction say about our own survival? These are not just academic questions. They shape our identity. The knowledge that we share a small percentage of our DNA with Neanderthals is a tangible link to these ancient relatives. It's a humbling reminder that our evolutionary path wasn't a straight line but a complex, branching river with many streams. These discoveries challenge the idea of human exceptionalism and connect us more deeply to the natural world and its cycles of life and extinction. So, how do these ancient bones shape our identity? They provide a narrative. Before these discoveries, our origin stories were often rooted in mythology and religion. While those stories hold cultural value, paleoanthropology gave us a scientific origin story, one based on evidence we can touch and measure. This narrative tells us that we are a species defined by adaptation, resilience, and change. It's a story of survival against the odds, of migration across continents, of the slow, steady development of intelligence and culture. This scientific saga empowers us. It shows us that our abilities to think, create, and cooperate are not accidents, but are the very tools that ensured our ancestors' survival and ultimately our own existence. We are the inheritors of this legacy. But here's a crucial point. Evolution isn't something that just happened in the past. It's an ongoing process, and we are living proof of it. The story of human evolution didn't end when Homo sapiens emerged. It's happening right now within our own bodies and across our global population. Let's consider some modern examples. Take lactose tolerance. Originally, adult humans couldn't digest milk. But as some of our ancestors began domesticating cattle, a genetic mutation that allowed for lifelong lactose digestion became a huge advantage. This trait spread rapidly through populations that relied on dairy farming. Today, whether or not you can enjoy a glass of milk as an adult is a direct result of recent human evolution, driven by culture and diet. It's a perfect example of how our biology is still adapting to our environment and our own inventions. Another fascinating case is the Bajau people of Southeast Asia, often called sea nomads. They have lived a marine nomadic lifestyle for over 1,000 years, spending much of their lives on boats and diving for food. Scientists have found that the Bajau have evolved significantly larger spleens than neighboring groups who live on land. Why does this matter? The spleen acts as a biological scuba tank storing oxygenated red blood cells. A larger spleen allows them to hold their breath and stay underwater for much longer periods. This is a clear, contemporary example of natural selection at work in a human population, a direct adaptation to a unique lifestyle. Even our resistance to diseases is a product of ongoing evolution. As humanity has faced new pathogens, from the Black Death to modern viruses, our immune systems have been under constant selective pressure. Genes that offer even a slight advantage in surviving an epidemic can become more common in subsequent generations. The genetic diversity in our immune systems today is a living library of the diseases our ancestors survived. We are constantly co-evolving with the microorganisms around us. These examples show that we are not the endpoint of evolution. We are a work in progress. The same forces that shaped our ancestors' natural selection, genetic mutation, and adaptation are still sculpting our species. Understanding this helps us reframe our perspective on humanity. We're not static beings but a dynamic, ever-changing species on a long journey. The challenges we face today, from climate change to new diseases, are the selective pressures that will shape the humans of the future. The story written in ancient bones is not over. A new chapter is being written with every generation. So why do these bones, these echoes from the deep past, still matter so much today? Because they hold the keys not only to our past, but also to our future. They are more than just scientific curiosities. They are a source of wisdom. Firstly, they teach us about resilience. The human lineage has survived ice ages, catastrophic volcanic eruptions, and dramatic shifts in climate. Our ancestors were the ultimate survivors. By studying how they adapted by changing their diet, their technology, or their location, we can learn valuable lessons for navigating our own environmental challenges. The fossil record is a testament to the fact that adaptation is our greatest strength. In a world facing climate change, this is a message we desperately need to hear. Secondly, these discoveries promote a sense of global unity. When you look at a 1.5 million-year-old hand axe from Africa and a 50,000-year-old cave painting from France, you realize that the human story belongs to everyone. Paleoanthropology erases borders. It reminds us that our modern divisions, nationality, ethnicity, religion, are incredibly recent and superficial compared to our shared deep history. We all descend from a small population of ancestors who began this incredible journey. This shared heritage is a powerful foundation for building a more connected and empathetic global community. Furthermore, studying our evolutionary past can provide critical insights into modern human health. Why do we have back problems? It's partly because our spines are still adapting to the stress of walking upright. Why are wisdom teeth often a problem? Because our jaws have gotten smaller as our diets have become softer. Many of the chronic health issues we face today have their roots in our evolutionary history. Understanding this mismatch between our ancient biology and our modern lifestyle can help doctors and scientists develop better strategies for promoting health and well-being. Finally, these bones inspire wonder. They connect us to something epic, a story far bigger than our own individual lives. Holding a fossil tool that was last touched by another human tens of thousands of years ago is a profoundly moving experience. It sparks curiosity about who we are and what it means to be human. This sense of wonder is the engine of scientific discovery and artistic creation. It fuels our desire to explore, to learn, and to understand our place in the universe. In the end, the living echo of ancient bones tells us that we are part of an unbroken chain of life. We are the current guardians of a legacy that began millions of years ago. These fossils are not just about the dead. They are about the living. They are about us. They challenge us, they unite us, and they inspire us to think about the future we are creating for the generations who will one day look back at our time. Thank you so much for joining me on this journey through time. If you found this fascinating, please like this video, subscribe to the channel, and hit that notification bell so you don't miss our next exploration. What part of our ancient past amazes you the most? Let me know in the comments below. See you next time.